A variable frequency drive, VFD-driven process gas compressor, is a crucial component in oil and gas upstream processing facilities. These compressors help in managing gas from low pressure, LP, and medium pressure, MP stages to high pressure, HP stages, facilitating gas injection and export. Here's a detailed process description of such a system. Hasher components and functionality. 1. Low pressure LP and medium pressure MP process gas compressors. Function. These compressors increase the pressure of the gas from the LP and MP stages of the production process. VFD integration. VFDs are used to control the speed of the compressor motors, allowing for precise control of gas flow rates and pressures. Multi-stage compression. The gas may go through several stages of compression, where each stage further increases the gas pressure. 2. High-pressure HP gas compressor. Function. This compressor takes gas from the LP and MP stages after being compressed to a higher pressure and further increases the pressure to a level suitable for gas injection or export. VFD integration. VFDs ensure that the compressor operates efficiently at varying loads and process conditions. Detailed process flow. 1. Gas collection. Gas from the production wells enters the facility at various pressures. LP gas typically comes from initial separation processes, while MP gas may come from intermediate separation or other processing stages. Initial compression, LP and MP stages. LP compressor. The LP gas is routed to the LP process gas compressor. The VFD adjusts the motor speed to maintain the desired outlet pressure and flow rate. The gas is compressed to an intermediate pressure. MP compressor. The MP gas follows a similar process where it is compressed by the MP process gas compressor. The VFD adjusts the motor speed based on process requirements. 3. Cooling and separation. After each compression stage, the gas is typically cooled to condense any liquids and remove heat generated during compression. The gas-liquid mixture is sent to separators to remove condensed liquids before entering the next stage of compression. 4. High-pressure compression. The gas from the LP and MP stages is combined and sent to the HP process gas compressor. The VFD on the HP compressor adjusts to maintain the desired discharge pressure and flow, optimizing energy consumption and ensuring stable operation. The gas is compressed to a high pressure suitable for the next stage of the process. 5. Gas injection and export. Gas injection. Some of the high-pressure gas is directed to injection wells for enhanced oil recovery or reservoir pressure maintenance. Injection pressures are maintained precisely using the VFD to adjust compressor output. Gas export. The remaining high-pressure gas is processed further, if necessary, and then exported via pipelines. Export pressures are similarly managed using the VFD to ensure consistency with pipeline requirements. Installation and design considerations. 1. Accuracy. Pressure and flow measurements must be accurate to ensure the compressors operate within safe and efficient ranges. High-precision instrumentation is used for monitoring and control. 2. Material selection. For sour service, presence of H2S, materials resistant to sulfide stress cracking and corrosion are selected. Common materials include stainless steels and nickel-based alloys. 3. Installation. Proper alignment of compressors and motors is crucial to avoid vibrations and ensure long-term reliability. Cooling systems must be effectively integrated to manage the heat generated during compression. 4. Control system. A sophisticated control system integrates the VFDs, pressure sensors, temperature sensors, and flow meters. The system ensures that each stage operates efficiently and responds dynamically to changes in process conditions. Benefits of VFD integration. Energy efficiency. VFDs optimize motor speed, reducing energy consumption compared to fixed-speed motors. Process control. Precise control over compressor output helps maintain desired process conditions, improving overall process stability. Reduced mechanical stress. Smooth starting and stopping of compressors reduce mechanical stress, extending equipment life. Flexibility. VFDs allow for easy adjustment to varying process demands without needing major equipment changes. Maintenance and monitoring. Regular inspections. Routine inspections and maintenance of VFDs, compressors, and associated instrumentation ensure reliable operation. Condition monitoring. continuous monitoring systems can detect early signs of wear or failure, allowing for proactive maintenance. This detailed process description outlines the role and operation of VFD-driven LP, MP, and HP process gas compressors in an upstream crude oil processing facility, highlighting the integration of VFD technology for enhanced control and efficiency. Here is a detailed technical explanation of the loops from suction, discharge, and anti-surge control that a process or instrument engineer needs to understand for a VFD-driven process gas compressor in an oil and gas processing facility. 1. Suction pressure control loop. Purpose: to maintain a stable suction pressure to the compressor, ensuring efficient and safe operation. Components: pressure transmitter, PT, measures the suction pressure of the gas entering the compressor. Controller, PID, processes the pressure signal and determines the necessary adjustments. Control valve, CV, regulates the flow of gas to maintain the desired suction pressure. Variable frequency drive, VFD, adjusts the compressor motor speed to maintain the desired suction pressure. Operation 1. Pressure measurement. The PT located at the compressor suction line measures the suction pressure and sends the signal to the controller. 2. Signal processing. The PID controller compares the measured pressure with the set point and computes the error. 3. Control action. The controller adjusts the control valve, or VFD, based on the error signal. If the suction pressure is too low, the VFD increases the motor speed, raising the gas flow rate into the compressor. Conversely, if the pressure is too high, the VFD reduces the motor speed. 4. Stabilization. The system continues to adjust until the suction pressure matches the set point. 2. Discharge pressure control loop. Purpose: to maintain a stable discharge pressure from the compressor, ensuring the downstream process requirements are met. Components: pressure transmitter, PT, measures the discharge pressure of the gas exiting the compressor. Controller, PID, processes the discharge pressure signal and determines necessary adjustments. Control valve, CV, regulates the flow of gas to maintain the desired discharge pressure. Variable frequency drive, VFD, adjusts the compressor motor speed to maintain the desired discharge pressure. Operation 1. Pressure measurement. The PT located at the compressor discharge line measures the discharge pressure and sends the signal to the controller. 2. Signal processing. The PID controller compares the measured pressure with the set point and computes the error. 3. Control action. The controller adjusts the control valve, or VFD, based on the error signal. If the discharge pressure is too low, the VFD increases the motor speed, boosting the pressure. If the pressure is too high, the VFD reduces the motor speed. 4. Stabilization. The system continues to adjust until the discharge pressure matches the set point. Number 3. Anti-surge control loop. Purpose: to protect the compressor from surge conditions, which can cause mechanical damage and operational instability. Components: flow transmitter, FT, measures the gas flow rate through the compressor. Pressure transmitter, PT, measures the suction and discharge pressures. Controller, anti-surge controller, processes flow and pressure signals to detect potential surge conditions. Recycle valve, RV, opens to recycle gas from the discharge side back to the suction side to prevent surge. Variable frequency drive, VFD, adjusts the compressor motor speed as part of surge control actions. Operation 1. Flow and pressure measurement. The FT measures the flow rate and PTs measure the suction and discharge pressures. These signals are sent to the anti-surge controller. 2. Signal processing. The anti-surge controller continuously monitors the flow and pressure conditions to detect proximity to surge. 3. Control action. If a surge condition is detected, e.g., a sudden drop in flow rate at high pressure, the controller opens the recycle valve to recycle some of the discharge gas back to the suction side, preventing the compressor from surging. 4. VFD adjustment. The VFD may also be adjusted to decrease the compressor speed, reducing the pressure ratio and avoiding surge. 5. Stabilization. The system continues to monitor and adjust until the compressor operates within safe parameters, preventing surge. Control strategies and tuning. Detuning. Proper tuning of PID controllers is critical to ensure responsive and stable control loops. Tuning involves setting the proportional, integral, and derivative gains to achieve desired performance without oscillation or excessive delay. Feed-forward control. In some cases, feed-forward control is used in conjunction with feedback control. This involves predicting process disturbances, e.g., changes in gas flow, and making preemptive adjustments to maintain stability. Redundancy and safety. Redundant instrumentation and control systems are often employed to enhance reliability and safety. Safety systems, such as emergency shutdown systems, ESD, are integrated to shut down the compressor in case of critical failures or unsafe conditions. Detailed loop schematics. Suction pressure control schematic. Suction line, PT, PID controller, VFD control valve, compressor inlet. Discharge pressure control schematic. Compressor discharge, PT, PID controller, VFD control valve, downstream process. Anti-surge control schematic. Compressor suction and discharge, PTs and FT, anti-surge controller, recycle valve, suction line, anti-surge controller, VFD adjustment, compressor speed control. Understanding these control loops is essential for process and instrument engineers to ensure the efficient, safe, and reliable operation of VFD-driven process gas compressors in upstream oil and gas facilities. When integrating a new compressor into an existing system for load sharing with existing compressors, several modifications are required to ensure proper control strategies and loop configurations. The goal is to maintain efficient operation, prevent surges, and balance the load between compressors. Here's a detailed explanation of the necessary modifications and their impact on control strategies and loop configurations. #1 Control Strategy Modifications. A. Master-slave control. Implement a master-slave control strategy where one compressor, master, dictates the operating conditions while the other compressors, slaves, follow. The master compressor's control system sends set points to the slave compressors to balance the load. B. Load-sharing algorithms. Develop load-sharing algorithms that distribute the total gas flow demand equally or based on the capacity of each compressor. Algorithms ensure that no single compressor is overloaded while others are underutilized. C. Synchronization. Ensure that the startup, shutdown, and operational synchronization of compressors are managed smoothly. Synchronize VFDs to adjust motor speeds of multiple compressors in unison. 2. Loop configuration modifications. A. Suction and discharge pressure control. Modify suction and discharge pressure control loops to include the new compressor. Implement a centralized control system to coordinate pressure set points across all compressors. Add additional pressure transmitters, PT, and control valves, CV, as necessary for the new compressor. Anti-surge control. Update the anti-surge control system to incorporate the new compressor. Ensure the anti-surge controllers for all compressors are interconnected and can communicate to prevent simultaneous surge conditions. Add new flow transmitters, FT, pressure transmitters, PT, and recycle valves, RV, for the new compressor. 3. Instrumentation and control system integration. A. Control system architecture. Expand the distributed control system, DCS, or programmable logic controller, PLC, to accommodate the new compressor. Ensure the control architecture supports seamless integration of the new compressor's control loops. B. Instrumentation. Install new pressure transmitters, PT, flow transmitters, FT, temperature transmitters, TT, and control valves, CV, for the new compressor. Ensure compatibility of new instrumentation with the existing control system. C. Communication protocols. Update communication protocols to ensure real-time data exchange between the control systems of all compressors. Use protocols like Modbus, Profibus, or Ethernet IP to facilitate communication. #4 Impact on control strategies and loop configurations. A. Load sharing and balancing. The load sharing algorithm adjusts the set points of each compressor to distribute the load. The master controller monitors overall system demand and dynamically allocates set points to each compressor. Ensure the VFDs of all compressors are coordinated to maintain balanced operation. B. Coordinated anti-surge protection. Anti-surge controllers must communicate to prevent cascading surges. Implement interlock systems to ensure that if one compressor approaches surge, other compressors adjust their operations to compensate. Configure the anti-surge control to activate recycle valves selectively based on the operational status of all compressors. C. Suction and discharge pressure management. Centralized control ensures uniform suction pressure across all compressors. Implementing shared control loops requires precise tuning to avoid conflicts and ensure stability. Adjust control valves and VFDs based on combined feedback from all suction and discharge pressure transmitters. D. Energy efficiency. VFDs ensure that compressors operate at optimal speeds, reducing energy consumption. Load-sharing algorithms contribute to energy efficiency by preventing any single compressor from running at full capacity unnecessarily. Detailed loop configuration schematic, suction pressure control, multiple compressors suction lines, PTs, central PID controller, VFDs, control valves, compressor inlets. Discharge pressure control, compressors discharge lines, PTs, central PID controller, VFDs, control valves, downstream process. Anti-surge control, compressors, suction and discharge lines, PTs and FTs, central anti-surge controller, recycle valves, suction lines, central anti-surge controller, VFD adjustments, compressor speed control. NAR 6 implementation steps. Step 1. Evaluate the existing system's capacity and control architecture. Assess the current load, control loops, and instrumentation. Identify points of integration for the new compressor. Step 2. Design the control strategy and loop configuration. Develop a master-slave or load-sharing control strategy. Design the loop configuration for suction, discharge, and anti-surge control. Step 3. Procure and install necessary instrumentation and control hardware. Install additional PTs, FTs, CVs, RVs, and VFDs. Ensure compatibility with the existing system. Step 4. Integrate and test the new control system. Integrate the new compressor into the existing DCS PLC. Perform comprehensive testing and tuning of control loops. Validate the load sharing and anti-surge control algorithms. Step 5. Commission the new compressor and monitor performance. Gradually bring the new compressor online and monitor its performance. Adjust control parameters as needed to ensure stable and efficient operation. By following these modifications and considering the impact on control strategies and loop configurations, a process or instrument engineer can successfully integrate a new compressor into an existing system, ensuring efficient load sharing and reliable operation. When integrating a variable frequency drive VFD into the control system of a compressor, there are several key aspects to consider, including loop control parameters, interfaces with the motor control center MCC, signals to the distributed control system DCS, operational control set points, vibration monitoring, and process side integration. Here's an in-depth look at each of these elements. 1. Typical VFD loop control parameters. A. Speed control. Set points, or RPM, desired speed of the motor compressor. Feedback PM, actual speed of the motor compressor, typically from an encoder. B. Torque control, set point NME, desired torque output of the motor. Feedback, actual torque output measured by the VFD. C. Current control, set point A, desired current supplied to the motor. Feedback A, actual current used to protect against overloads. D. Voltage control, set point V, desired voltage supplied to the motor. Feedback, actual voltage ensuring motor operates within safe limits. E. PID control parameters, proportional P, gain that determines the reaction to current error. Integral I, gain that determines the reaction based on the sum of past errors. Derivative D, gain that determines the reaction to the rate of change of error. 2. Interfaces with MCC, motor control center. A. Signals to MCC, start-stop commands, digital signals from the DCS to initiate or halt the motor. Speed reference, analog or digital signal, typically 4 to 20 milliamps or 0 to 10 volts, indicating desired motor speed. Fault signals, digital signals indicating motor or VFD faults to the MCC. B. Signals from MCC, status feedback, digital signals indicating motor status, running, stopped, fault. Current feedback, analog signal, 420 milliamps, indicating motor current. Voltage feedback, analog signal indicating motor voltage. Speed feedback, analog or digital signal indicating actual motor speed. Now 3. Interfaces with DCS, distributed control system. A. Signals to DCS. Speed set point. Desired speed for the VFD provided by the DCS. Torque set point. Desired torque if torque control is utilized. Start-stop commands. Commands to start or stop the compressor. B. Signals from DCS. Speed feedback. Actual speed of the compressor. Current feedback. Real-time motor current. Voltage feedback. Real-time motor voltage. Vibration data. Real-time vibration data from the compressor. Temperature data. Real-time motor and compressor temperatures. Fault alarms. Real-time fault and alarm status. Now 4. Compressor control system, operational control and set points. A. Operational control. Automatic mode. Compressor operates based on predefined set points and process conditions. Manual mode. Operator can manually control the compressor speed and other parameters. Emergency stop. Immediate shutdown in case of emergency. B. Set points. Speed set point. Desired compressor speed. Discharge pressure set point. Target discharge pressure of the compressor. Suction pressure set point. Target suction pressure if applicable. Flow rate set point. Desired gas flow rate through the compressor. Torque set point. Desired motor torque. 5. Vibration monitoring of compressor. A. Vibration sensors. Accelerometers. Measure vibration levels in terms of acceleration. Velocity sensors. Measure vibration velocity. Displacement sensors. Measure vibration displacement. B. Data collection and analysis. Vibration data acquisition. Sensors send data to a vibration monitoring system or directly to the DCS. Analysis. Real-time analysis of vibration data to detect anomalies or trends indicating potential issues. Alarm levels. Predefined vibration levels that trigger alarms and potentially shut down the compressor to prevent damage. 6. Process side integration. A. Process measurements. Pressure transmitters, PT, measure suction and discharge pressures. Flow transmitters, FT, measure gas flow rates. Temperature transmitters, TT, measure gas and compressor temperatures. B. Control loops. Suction pressure control loop ensures stable suction pressure by adjusting the compressor speed or flow control valves. Discharge pressure control loop maintains desired discharge pressure by adjusting compressor speed or downstream control valves. Flow control loop manages gas flow rates to meet process requirements. C. Control integration, PID controllers, use process measurements to adjust set points and control actions. Communication protocols use standardized protocols, e.g. Modbus, Profibus, for seamless integration and real-time data exchange between the VFD, DCS, and compressor control system. Typical loop configuration. A. Suction pressure control loop. Suction line, pressure transmitter, PT, PID controller in DCS, VFD speed control signal, compressor motor. Discharge pressure control loop, discharge line, pressure transmitter, PT, PID controller in DCS, via speed control signal, compressor motor. C. Vibration monitoring loop, compressor vibration sensors, vibration monitoring system or DCS, alarms and shutdown logic. 8. Integration with other systems. A. Safety systems, emergency shutdown ESD, integration with ESD systems to ensure safe and rapid shutdown during critical conditions. Overpressure protection, ensure the system is protected against overpressure conditions using relief valves or similar mechanisms. B. Maintenance and diagnostics, predictive maintenance, use vibration and other real-time data to predict and prevent failures. Diagnostics, advanced diagnostics through DCS to identify and troubleshoot issues. By understanding these parameters and interfaces, a process or instrument engineer can effectively design, integrate, and operate a VFD-driven compressor system, ensuring optimal performance and reliability.